Our rocket has 3 rings, 2 for the inhabitants and 1 for manual labour. Each ring will be 10 metres in diameter. The living rings have a 2-metre corridor throughout the entirety of the structure, providing ample space for any transport of goods or people. Each one will have the capacity for 150 people, where each individual gets their own room to make the crew more comfortable, as mental health is crucial on long space hauls. There will also be a docking port in alternating rooms so that other vessels can dock. The excess space will be for crew services, for example, toilets and leisure, and also storage. There are many small modules that can be attached to the living ring in order to help maximise storage capability. The work ring has 1 floor to maximise space for production. Each ring speed will be adjusted by RCS monopropellant thrusters in order to replicate the gravity of the current location to help the crew adapt before arrival. The standard speed of each ring will be 17.1 meters per second for the living rings, 3.4 RPM, and 10.46 meters per second for the work ring, 5.5 RPM, in order to replicate Mars gravity to help prevent muscle deterioration. In the centre of the structure is a 40-metre diameter cylinder that will be used for human services such as entertainment, which don't require gravity. We chose this because it frees up space in the living ring for storage, as it is easier to store goods in gravity. Lower down in the rocket we have a storage overflow area just in case we need to take more than planned. All small to medium packages will be velcroed in, whereas large, more unstable ones will be strapped in and tightened. We also have an autonomous cockpit that is occasionally manned by a small crew. The majority of maneuvers, trajectories, and gravity assists will be controlled from nearby colonies via ground control.
Due to the long duration of the flight, we need to be producing food to limit the amount of weight of the MREs we're carrying. However, we cannot produce all of the food for the crew, as this would take up way too much space, so we'll have to find a balance for it with MREs. The best balance we found is for a quarter of the crew to get 1 fresh meal a day on a rota. To find out how much space we needed, I worked out a rough meal plan, and from that, using total crop yields, I worked out the amount of plants needed, and then the amount of space needed to grow those plants. We will grow our food using an aeroponic system, as it is very efficient and reduces water loss by 96 to 98%.
In the life support systems, we will be using artificial intelligence to keep the concentrations of each gas correct. Plants will release about 1,500 litres of oxygen per hour, but humans altogether will inspire and expire about 15,000 litres per hour, so we do need other methods. We'll use chemical oxygen generators that will use sodium chlorate and iron powders that will release oxygen via chemical reactions. They will be ignited smoulders at 600 degrees Celsius, and there will be indefinite shelf life if they are stored properly. Thermal decomposition will release oxygen by burning iron and supplying heat. We will need a sustainable method to remove carbon dioxide because plants will do just a bit of it. We will use zeolites that have open pores to suck in the carbon dioxide, and we will also use lithium hydroxide scrubbers that will absorb it as well, and we will use these methods in large proportions to get rid of enough carbon dioxide to get it to a concentration of about 0.04%.
To power these systems, we've decided to have 2 main sources of power and 2 secondary sources of power. As per the specification, the Satire 4 engine will provide a minimum power output of 2 kW and a maximum power output of 100 kW. To push the ship, we've decided to use 25 Satire engines to bring us to a power output of 50 or 2,500 kW. These 25 boosters thrust the ship in conjunction with 6 iron engines, which give a constant force saving fuel and gravity assist with nearby celestial bodies. By entering orbits and timing specific burns, the ship can be made to enter heliocentric orbits and intersect with the destination body. A secondary source of power is the kilopower reactor, which will provide a power output of 30 to 40 kW, a large increase from the power output in 2020. This means the ship will have a plentiful supply of electricity to support its many systems. Should one power system fail, the other will power the ship enough until repairs can be made. A secondary source of power is the ship's foldable solar panels covered in perovskite crystals, increasing the percentage of solar energy converted from 23% to 27.3%. This means when the ship is at a distance 1 astronomical unit or less from the Sun, these panels can be deployed in a similar manner to the central one will appear. Though sizes differ, the mechanism will not be too dissimilar. In the event of a solar flare, which could deactivate electrical systems, our warning system will be triggered. This warning system will be housed in a satellite around Mercury, which will also act as a future common satellite for the Cecilia settlement. When the ship detects this signal, electrical systems must be turned off, and nickel metal hydride batteries can power critical systems in the meantime, which generally lasts from 10 to 20 minutes.
The batteries could be considered as the secondary power source and would only be used for emergencies,